JW Physics. I'm Mr. McConnelly, and today we're going to talk about quantum theory. In 1926, Erwin Schrödinger came up with some postulates or ideas that helped concrete the quantum theory. He said that matter is wave and particle in nature at the same time, which is odd when you think about it, because you think of a particle as a little object like a ball that can bounce off of something, and you think of a wave as, you know, a little water wave, energy traveling through matter. But matter can be both, wave and particle in nature. And so, when we're talking about electrons, this becomes especially true. And it's impossible to know the position and the momentum of an electron at the same time. If you figure out one, it makes it so you can't find the other. And this is very confusing. And people at this time, like Bohr, had come up with the Bohr model of the atom, where the nucleus was in the middle and the electrons were in orbitals around the outside. But there were problems with that, and Schrödinger wanted to take it to the next level and make it much more accurate and predictable so that you could find out a lot more information. And what he really ended up coming up with is the quantum model. And the quantum model predicts the probability that an electron will be in a certain location. So it predicts by probability an electron's location. And actually these are, you almost want to think of it of like waves of probability. So there's regions or waves that they say, oh, the probability is higher in this location. And those waves of probability actually are called electron clouds. You can kind of, I should put more space there, electron clouds. So you can kind of think of it like, well, we know the electron is here-ish, okay, and it's in this cloud area, but you can't really nail it down exactly, but that's a lot better than what we could do before, because before, when we were using the Bohr model, we could just say it was in this orbital and not in a specific location. Then, from this, a whole field called quantum, can't write today, mechanics emerged. Quantum mechanics. Now, quantum mechanics usually stirs fear in the hearts of all college physics majors because it's just a class that's difficult. And what quantum mechanics basically is, it's the study of the properties of matter and the wave properties of this matter. So you take what we're talking about here with these probabilistic representations, and you apply this to different matter. And what it led to, what it eventually leads to, is the development or finding out lasers. Now laser, I don't know if you have realized this before, laser is a word we use like, because you know, a lot of people have lasers nowadays. You can get laser pointers and green lasers and purple lasers and red lasers. And you do laser surgery, LASIK eye surgery, and et cetera, et cetera. And lasers are very useful in a lot of different areas. But do you know what laser actually stands for? It stands for light amplification stimulated emission of radiation. So, I'll say that a little slower. It's light amplification stimulated emission of radiation. And it all came from the field of quantum mechanics, because once they realized that they could get these waves of probability, they realized also that they could take light and they could get it to be coherent. And coherent means in discrete packets or waves where all the light starts lining up like this. So quantum mechanics is an upper level physics topic, and if you do take college physics and you get into quantum mechanics, there's a lot of math involved in it. And it's really interesting stuff. But for today, as a high school student, that's all you need to know, so physics.